And another very important theorem, and both of these are very much related, is that if you have if A and B are both, they have to have the same dimension, n by n, so they're both square matrices, then, well, if we multiply the two matrices together, we get an n by n matrix, and we can calculate its determinant. And the determinant is a number, and you can always multiply two numbers. And it says that this determinant operation is multiplicative. So this is also a very important result here. Okay, so the idea behind these, I won't prove them, but the idea behind these two theorems is just that. So we can prove these by so remembering that every invertible matrix A is a product of elementary matrices. So every invertible matrix is a product of elementary matrices. So if you take some matrix, so if A, then we can write it as a bunch of elementary matrices. You have some kth elementary matrix, another elementary matrix, da 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 da. So there are k different elementary matrices. These correspond to the row operations. These are like the row operations that you can use to turn the identity matrix into A. So if a matrix is invertible, then you can perform row operations to turn it into the identity, and you can reverse that process and turn the identity matrix into the matrix A. So we remember this fact here. So that's like one of the first things we need. We remember this fact here, and then the second thing we can do is we can analyze. Then we can analyze the effect of performing an elementary row operation on calculating determinants. And from that we can conclude that we can see that that the determinant of an elementary matrix times an arbitrary matrix is just the determinant of the elementary matrix times the determinant of B. And from that we can just put everything together. So this implies, so from here we get both theorems. Both theorems. Okay, because if the matrix is invertible, we get both of these theorems both theorems. So how can you see that? So if the matrix is invertible, then you can write it like this, and that implies that its determinant, the determinant of A, is equal to the determinant of all these elementary matrices. And it's easy to see that the determinant of elementary matrices are not 0. Both theorems, you can see that the determinant of an elementary matrix is never equal to 0. And so if it's invertible, then its determinant is non-zero. And then similarly, you can always write, if you want to calculate the determinant of A times B, you can write A as a product of elementary matrices and B as a product of elementary matrices. And so you're done. So these are two very important properties of determinants. So let's do an example. So if A is the matrix 1, 2, 2, 3, 1, 0, 1, 2, 4, 6. Then we see that row 1 and row 3 are proportional, right? Because row 1 is 1, 2, 3, and row 3 is 2, 4, 6. So that's equal to 2 times row 1. And therefore, the determinant of A is equal to 0, and therefore A is not invertible. So that's an example. If the determinant is equal to 0, then the matrix is not invertible. So let's do another example. Say A is the matrix 3, 1, 2, 1. Let's say B is the matrix -1, 3, 5, 8. Then let's just calculate the determinants. So what's the determinant of A? Well, that would equal 3 times 1 minus 2. That's equal to 1. And the determinant of B, that's equal to minus 8 minus 15, which is equal to minus 23. Okay, what else can we do? So we know what the determinants are. Now, let's consider the product. What happens if we do A times B? So that's 3, 1, 2, 1, multiplied by minus 1, 3, 5, 8. So we're just going to do matrix multiplication. So we get, that gives us negative 3 plus 5, that gives us 2. The 2, 1 entry, that gives us negative 2 plus 5, that gives us 3. Now let's do the 1, 2 entry, that is 3 times 3 is 9, plus 8, that gives us 17. And the 2, 2 entry over here, that gives us 3 times 2 is 6, plus 8 gives us 14. So now that we have that, let's just calculate the determinant of AB. So that's the determinant of this 2 by 2 matrix, 2, 17, 3, 14. That's a 17. And again, what is that equal to? That's 2 times 14 is 28, minus 3 times 17, 45, 46, 47, 48, 49, 50, 51, and that's equal to minus 23. Hopefully I made a mistake, I'm bad at arithmetic. Okay. So you can see that, and of course 23, sorry, I just wanted to, and of course 23 minus 23 is of course the same thing as minus 23 times 1. This is kind of an extreme example, and of course that's determinant of A is 1 times the determinant of B. So we have this equality here. That's just showing you this multiplicative property of determinants, which is very powerful. All right, here's another result. If A is invertible, then that means A inverse is invertible. We can construct A inverse, and we can take its determinant, and its determinant is equal to 1 over the determinant of A. And this is very easy to prove, so we can just prove this. We know that A is invertible. That means that A times A inverse is equal to the identity matrix. And then by the property of the determinant, it's a multiplicative thing, so that says that the determinant of A, well, let me just be more careful. So we have this equality here, so we can apply the determinant function to each side. So we get A times A inverse, that's equal to the determinant of the identity matrix. The determinant of the identity matrix is 1, so this is 1, and then we have this multiplicative property, so that says that the determinant of A times the determinant of A inverse is equal to 1. And then we can divide both sides of this equation, and we see that the determinant of A inverse is 1 over the determinant